Hello, my friend. My name is Anton from containerised.com, and we continue our OpenStack series. Today would be the last theoretical part before we start building our own OpenStack services or OpenStack cloud. We talked about the microservices in the context of building OpenStack cloud. But before we talk about that, let's talk a little bit about what the service in general, when we talk about anything, any application, any web application, any Linux service, daemon, and so on and so forth. If you think about the way how we are operating with our computers, we could think about any application that we run is some sort of service, right? Especially any application that we can launch and interact through some sort of UI or API. So service as an abstract term, which basically means something that's doing for us some job. At a very, very high level, we could split it into two parts. The interface, which could be either UI, user interface, where we are through the web UI or graphical user interface, could click or type and get some responses, or application programmable interface, which is, or API, which is where the application is talking to each other, or we using some scripts or tools like, for example, Postman and any other, will make a request. Upon making the request to the applications or services interface, it triggers some job in the background. Here you see the one useful job. However, the structure of the service could be much more complicated. It could be multiple jobs. It could be some further, as we were discussing previously in our practical OpenStack series, load balancers, front end, back end, and so on and so forth. So, but you got the idea. So service is doing for us some job. It has some parts. So if you think about, okay, service is an application, what we need to have for the application to run on a server. First of all, the application itself, we need to install it, right? And when we install the application, we install the main package, how it is called in the Linux of the application, and also the dependencies. Dependency meaning the packages which our application requires system to have in order for the target application to be able to work. So for example, if we install the Python as an application, we'll install approximately 50 to 80 more dependencies which our system need to have under the hood. So for each of the applications, so one of the important things, each of the application has its own version of the application which we are installing and all the dependencies. This point will be crucial when we talk about the advantages and disadvantages of service management in the standard way. So if you talk about the application which can be interacted by a user, it means that the application need to have some sort of port, so TCP or UDP port on which we could connect. So it means so we need to have these resources available, so networking resources. Not talking about the CPU and memory, obviously you need to have some CPU and memory for the application to be able to run. And also we need to be able for the application, the users, like the users who are interacting with the application, as well as some functional users for the application to be created, and corresponding permissions shall be granted. It brings us to the example. So how we basically install the application or services in the Linux. Example on the Debian-based distributive, meaning the Debian or Ubuntu, to install the application as simple as sudo apt-get update, first of all, in order to refresh the headers of all the available application, and then we install it using the same tool. So basically apt-get is called package manager. We install corresponding application. Obviously, if you're a little bit familiar with Linux user, yeah, there are a bunch of other things that we need to do. We could install the application using the dep package. We need in certain cases to add extra repositories and so on and so forth. Obviously, there is the process of installation of the application could be much more complicated than this. However, you're getting the point. You still install the application directly in your operating system. And when we install like package 1 and 2, there is quite a high probability there was a lot of other dependency packages installed together with our one. Same package manager, but So same functionality of the package manager, but different tool itself. For the CentOS, that have a Rocky Linux is called DNF. Other Linux distributions might have some other package managers, but in general, the idea is the same: sudo DNF or sudo apt-get, update, and then install. We get the application installed if these three things that we were mentioning beforehand were available. So if it was possible to install the applications, if we had permissions to do that, because by default, not all the users are permitted to install the applications. Then if we have the corresponding network resources in order to publish the application, make sure it is available, and there were no clashes with the dependency. So the clashes of the dependency is quite an interesting thing. So if you think about the deployment of the applications, installing their services on Linux in this way, the benefits that we have is it is relatively easy to do. We don't need to have any extra tool. We use package manager, which is inherently part of the Linux. Basically, each Linux, like Ubuntu, Debian, CentOS, Red Hat, Rocky, and others have package manager installed. You don't need to have any extra tool, therefore, to install and manage your packages. There is a number of drawbacks if you're willing to manage application this way. Namely, there might be the clash between the dependency. What does it mean? So if I'm installing the package which require dependency, say package like GCC, one of the most popular packages which is used by, which contains C binding for a lot of programming language, including for the Python, and it would require the certain version, for example, version 2.3. And I'm installing another application that would be saying, I need to have the version of this tool. I'm installing some legacy application, for example, 1.8, or basically anything less than 2. And then I cannot have the two applications installed, because if I'm installing one application and it's telling me that, okay, requirement of the GCC should be more than 2, and another application saying the requirement of the GCC should be less than 2, I can install only one of them, or I can install probably both of them, but only one of them would be working because GCC version would be suitable only to a single one. And when we think about the complex setups, complex application, there might be much more such dependency clashes. The same dependency clashes existing when we are managing the Python-based applications and others. This is just the nature how their services being done in Linux. With adding more services, obviously the probability of the dependency clashes is increasing, and the only solution that used to be in this way would be to run either VMs, which is obviously quite an extra overhead, or have a simply physical separated service for different applications, which is even worse overhead. So, and this is on the stage, and this is a point when the stage comes containerization. The idea of the containerization is very straightforward, and I think very appealing. How you could create the dedicated namespace, in fact, the bundle of namespaces, where we could install its own dependencies in the runtime. So the container, to put it very simple, is a namespace at the collection of the processes, chilled namespaces, network namespaces, and global and mount namespaces, where from the container perspective, you see only things existing in your namespace, and if your operating system, you see the things outside of the container and things from the target container. So it allows us to create the separation for each application to have its own runtime, and therefore to be able to install its own dependency directly inside the container. So that solves the problem with the dependency clashes. It also provides a degree of security where each and every container has its own namespace, and therefore there is no direct communication between them besides the networking, which is, again, could be firewalled and filtered if needed. Originally, the containers were supposed to be short-living jobs, but in many cases, we run as containers long-running services like databases, time series databases, Grafana, like Prometheus, Polars, and other things. And therefore, we would like to have the persistent storage. It's also possible to achieve that with containers. So altogether, the idea of the container is that I can containerize the service. The idea is then service is deployed within the container. Then normally we would have one container, one service. Not going really too deep into the details, the container is running on the same kernel as your operating system. So they share the kernel. As such, there is no that huge overhead compared to the case where we run the VMs, and it provides us possibility to like really containerize each and every service. This approach is often called the microservices. It doesn't equal, like microservices doesn't equal containerization. It just, containerization is one of the ways how microservices can be deployed. So, and build of the application within the containers or putting our service in the containers gives a number of benefits. First of all, it creates a very clear separation between the services and the infrastructure. So everything that is doing some useful job, even if it's a job related to the infrastructure, will be containerizing. So on the other hand, our underlying infrastructure host will be running only, say, Docker, and all the further applications, they are deployed inside as a containers. Each container has its own internal dependency. So I said all the containers sharing the same kernel, how each and every has a runtime in a sense, so that each and every container would have its own libraries, which is needed for the application to run. The amount of the library would be limited only to this application. Hence, we don't have that huge overhead of the installed extra dependencies. Obviously, the container is done right. There might be some different scenarios. And once you get some experience with the containers, you would feel like it is really easy to manage this. So in fact, a lot of the services that I'm deploying and what we are teaching for our students in the Zero to Hero network automation training, how to create your own containers, how to containerize your network automation services. Once you understand the approach and once you build a few containers, you'll figure out it's really easy approach. Obviously, everything comes at costs. In this case, the cost is that we need to have an extra tool, which is Docker itself. And ultimately, there is some degree of extra complexity, meaning we're not we're not installing the application directly on a host. We put in the container. It means we need to know how to do the networking towards the container, or which approaches we have. In terms of the networking, how to make the storage persistent, how to make sure we schedule containers to be up all the time, and so on and so forth. So, however, this complexity, once you learn how it is working, is relatively low, and the benefit, in my eyes, are quite significant. Now, having talked about that, in general, what service means and what containerization of services means, let's take a look how this is relevant to the OpenStack. So OpenStack consists from the amount of services, and the amount of the services depends on which amount of the project and services from the OpenStack we are deploying. And at a bare minimum, or let's say at the scope of the COA exam, or at the scope of what is normally being used in the network, we would be deploying about 8 to 10 OpenStack services. Keystone, the service for how it's called identity management. So this is the piece of the OpenStack which is responsible for creation of the users, projects, assigning the roles of users within the project, and all other things. As a glance, image service, so this piece of the OpenStack which is responsible for storing the like base images for the operating system, which we are using to deploy the user VMs. Nova, which is a compute service, which is one of the obviously key services of the OpenStack. This is the piece of the OpenStack which is responsible for creating and the general lifecycle of all the user VMs based on different hypervisors, predominantly KVM, but not only. Other hypervisors could be used as well. We have a Cinder, which is a block storage, which is responsible for creating values for the VMs. and communicating this over the iSCSI network or other type of the network. We have Neutron, which is a networking service, which is responsible for creating bridges, OpenStack, OpenVSwitch, or Linux bridges, or OVN, and other things. We have a Horizon dashboard, which is the UI for the OpenStack. We have a HID, which is a built-in orchestrator, which is allowing us, rather than through the UI or separated CLI commands, to create the what is called stack. So the collocation of the OpenStack resources in a like single run. We have also a Swift, which is object storage, and some others. So all of them consist further down from a multiple series. For example, talking about the Keystone. Keystone consists of the Keystone itself, API Keystone, and we have the interaction to the database and LDAP, which is another important thing. OpenStack in its work relies on a few non-OpenStack, how they called core components, such as MariaDB, a database where all the things about the OpenStack is stored, such as users, projects, VMs, networking pieces like bridges, VIX, LAN, server, security groups, and some other things. RabbitMQ, which is a messaging queue used for various applications, namely OpenStack services, to interact to each other. So each of these services obviously require certain dependency. In this case, I mean, in the case of the OpenStack, the vast majority of them are written in the Python. And when we talk about the Python, similar approach as we have explained about the Linux in general is applied, meaning for Python application to work, it needs to be the requirement fulfilled that the host where we run the Python application should have all the Python dependency installed. As a part of the setup, normally this dependency being installed. But the thing is, we need really to be sure that all this variety of extra packages installed. That's why the same approach of the containerization is quite logically fitting into the deployment of the OpenStack services, where we could deploy the core non-OpenStack services such as RabbitMQ, etcd, or MariaDB as a containers. We could deploy it as a redundant containers for multiple separated hosts and build a Galera cluster and other things, as well as the OpenStack core services themselves, such as Keystone, Keystone API, Glance API, registry, and so on. So technically, anything that you see in these boxes, either with a bold font or non-bold, this is all the elements, all the technical services run on the Linux host that could be containerized. So this is why, and this is the approach which we'll be deploying in our scenario when we get to the setup. All the OpenStack services themselves will be containerized, and communication with them is solely through the networking. However, microservices obviously is important not only for building OpenStack itself, but also to build your application further. And this is where probably the keyword Kubernetes is coming to the game. The vast majority of the modern application being built right now, being started to build, or at least considering being containerized. This is something that was called cloud native. Cloud native, in many cases, if not equal, but containerization, one of the parts of the cloud native things. And you could deploy containers directly on the bare metal services, or you could deploy the containers on the VMs. The benefit of deploying the containers directly on the bare metal, you don't have an extra layer of the middleware, but you need somehow to manage the provisioning of the services, installing of the operating system. You could have it with OpenStack Ironic. In this case, you could use OpenStack to manage your physical infrastructure and then deployment of user workload using Kubernetes on the bare metal services. Then we installed the Docker. We could install also CRI-OD, but Docker probably the most popular tool these days. And then we installed the Kubernetes to manage the Docker containers. Obviously, it's very simplistic explanation. The complexity of the setup is much more like big, but this gives you some point. And second one is we create the containers within the VM. So we deploy the VMs using the, for example, OpenStack Nova. Then within the container, within the VM we install the container on top, we create the Kubernetes to manage them. The idea is here that we could have multiple different services, might have different capabilities, but there is a like normalized layer between the setup of the containers on top of the operating system and underlying hardware. So this approach is used in many managed service Kubernetes providers where they prefer to use OpenStack as a middleware and VMs to deploy their user workload. So this is it for today. Thank you very much for the attention. Starting from the next session, we'll start looking at the practical aspects, how we can finally build our real world OpenStack lab with a hyper-converged cluster, and we'll start getting our hands dirty. Thank you very much for your attention today, and I hope to see all you soon. Take care, stay well, and goodbye.